Let's continue talking about substitution reactions, but let's switch gears now to talk about SN1 reactions. An SN1 reaction is a stepwise process. The first step in all SN1 reactions is for the leaving group to leave. In other words, I form a carbocation. And this is the slow step. So this is the rate limiting step. I can see that down here in this reaction coordinate, where here are my two starting materials, the alkyl halide and the nucleophile. The large activation energy is to go over to this first intermediate, which is my carbocation. So that's the slow step. The next step, which is step number 2, is actually very fast. My nucleophile then sees my carbocation and it attacks and it forms a new bond between them. This does, of course, imply that the nucleophile does have to go in and find the electrophile. So this chemical reaction is two-step. It has a carbocation intermediate. It's first order, meaning the slow part of the reaction is actually forming the carbocation, and then it's very fast. So my rate only depends on carbocation formation, so it is first order in my substrate only. Because I form a carbocation, that's going to be a trigonal planar carbocation, I can have my nucleophile attack from either side, so I'm going to form a racemic mixture. Equal amounts of R and S isomer are formed in this substitution reaction. Let's look at a real-life example. Here I have a tertiary alkyl halide, and I have a solvent. Okay, so the first thing that happens in a SN1 reaction is, again, we lose our alkyl halide to form a carbocation. But then what's our nucleophile going to be? Well, in this case, it's actually our solvent, because there's a lone pair of electrons in my methanol molecule, and it can act as a nucleophile and attack my carbocation. And so I form, in this case, I form my ether with my carbon here attached to 3 other carbon groups. So it's a tertiary ether. I'm also going to have my 2 anions that are formed. So I do have to have a lot of methanol, but being the solvent, we typically have a lot. Let's look at how this chemical reaction works, and let's take a look at it step by step. So because it goes through a carbocation, the first thing I need to do is start breaking this bond. Okay, so in other words, my leaving group starts to take on a much larger negative charge, and I actually break that bond to form a carbocation. And this carbocation has to be a stable intermediate in order for this process to go. And we know that tertiary carbocations are fairly stable species. The second step in my SN2 mechanism is for the nucleophile to attack the resulting carbocation. So in step 2, my nucleophile is typically the solvent. That's because, as we're going to find out shortly, an SN1 mechanism needs a weak nucleophile, and solvents like methanol and water and ethanol are weak nucleophiles. So I have a lone pair of electrons, they attack my carbocation. My resulting species here is actually a cation still. And so in order to form a neutral molecule, I need to remove that proton. And there is actually a third step in most SN1 reactions, and it is a deprotonation step, where my methanol now acts as a base instead of a nucleophile, and it attacks that proton, where these electrons, they'll go down to form my new lone pair in my resulting ether. And this is also a fast reaction. So let's look at this, putting it all together. I have a tertiary alkyl halide. I have my carbon-bromine bond break to form my carbocation, and notice this is a tertiary carbocation, so it's fairly stable. In this case, my solvent is water, so my water acts as a nucleophile, forming a bond between my electrophilic carbon and my oxygen. I still have to do one more step here to deprotonate that new species to actually form my neutral alcohol. Let's look at the reaction coordinate again. I have my alkyl halide and my nucleophile. My nucleophile has to be weak. There's a large activation energy to actually lose that alkyl halide, so it's a slow process. But my resulting carbocation has to be stable. In order to stabilize that carbocation, one thing we've learned is that I have more substituents on my carbon. So the more substituted that carbocation, the more stable it is. Once I formed a carbocation, I quickly react with my nucleophile in solution to form my substituted product. So slow step, fast step. Another criteria is that my nucleophile again has to be nearby, and they have to actually touch each other. Otherwise, there's an opportunity for the reverse reaction to occur, for my halide to reform a bond with my carbocation. Let's look at stability of carbocations and energy. If I have a reaction coordinate here, and this is for an SN1 reaction, here's my alkyl halide. To get to that first transition state and over to my first intermediate product, I need to have a stable intermediate, and tertiary carbocations are stable. Secondary are less stable, primary are much less stable, and methyl carbocations are usually not possible. The activation energy to get over that energy bump here is just too high to form the methyl carbocation. We have two effects that are stabilizing my tertiary carbocation. One is an inductive effect where my methyl groups on a tertiary carbocation are actually electropositive, and so they're pushing electrons away from them toward my carbocation, or my hyperconjugation effect, where once I make the carbocation, my methyl group out here, one of the bonds between my carbon and the hydrogen can actually overlap slightly, allowing to my electrons to have more space to be in. We call that hyperconjugation. So if I looked at stability from my energy diagram and from my model arguments here, tertiary carbocations are more stable than secondary, are more stable than primary, are more stable than methyl. So if I want to do an SN1 reaction, a tertiary alkyl halide is the most favorable. Let's look at some other stable carbocations. If I look and compare these two carbocations, okay, this one is a secondary carbocation, and this one is a secondary carbocation, but this one is allylic. I know I can actually have resonance stabilization because I can draw a resonance structure over here. I can flip those electrons down and move my carbocation over here. If I can draw resonance structures, I have a more stable carbocation. So this carbocation is more stable than this one. I can't draw any resonance structures here. If I look at these two molecules, I could also see that I have a carbocation in this case, which is a secondary carbocation. This one is also a carbocation that's next to two different atoms here, even though we technically wouldn't call it secondary, but it's next to a nitrogen with a lone pair. And so in this case, I could actually draw a resonance structure here and stabilize this carbocation. So if I have a alkyl halide that is allylic, I know it has a tendency to form carbocations, and it undergoes SN1 reactions more rapidly. The same thing here. If I have a alkyl halide next to a nitrogen, it undergoes SN1 reactions at a faster rate because I form a more stable carbocation. Let's look at some more trends in carbocation stability, and I've added a few here. So on the right-hand side here, I've drawn a bunch of different carbocations, and I've plotted them relative to their stability. The ones at the bottom are least stable, the ones at the top are most stable. Let's start down here at the bottom. If I have a methyl carbocation, that's going to be not stable. So I must have had a methyl alkyl halide to generate that. As I go to a primary carbocation, that's slightly more stable, but typically not stable enough to undergo SN1 reactions. If I go to a secondary carbocation or a primary allylic carbocation, both those are similar in stability. Those will undergo SN1 type of reactions. A little more stable would be a tertiary alkyl halide or a secondary allylic, or I could have a primary benzylic. Notice with these lone pairs of these electrons here in this aromatic ring, I could draw a bunch of different resonance structures. Resonance again implies stability. If I go here to a tertiary carbocation, that's allylic, or a benzylic carbocation, that's secondary, those are even more stable. And finally, the most stable in this list is a tertiary benzylic carbocation. This will undergo SN1 reactions very quickly. So I start with a tertiary benzylic alkyl halide. It loses its halogen to form this carbocation and then reacts with a nucleophile. We can also have inductively stabilized carbocations. This whole list here is actually secondary carbocations with a fluorine 2 carbons away, a chlorine, and a methyl group. This one would actually be the most stable. Let's see why that would be. If I have chlorine on there, that's electronegative. It's pulling electrons away from that carbocation, making it even less stable. And if I go to fluorine, it's more electronegative than chlorine. It's pulling electron density away from that carbocation and making it the least stable in this 3-molecule list. Also, a better leaving group will increase the rate of reaction. So if I look at leaving groups here, iodine, which is polarizable, is a better leaving group than bromine and chloride, but they are still very good. Then comes a molecule called tosylate, which we're going to talk about in a chapter coming up here. Water is a moderate leaving group, but it becomes better if we protonate it in an acid catalyst. Then fluoride is poor, and I keep on going down. As you notice, these ones here on the right are actually very good nucleophiles. They're not good leaving groups. Here's just some more words talking about the stability. As we briefly mentioned earlier, the nucleophile in SN1 reactions is typically the solvent, and we actually call these reactions solvolysis. That's an old term for SN1 reaction, and it's still used an awful lot. So in an SN1 solvolysis reaction, the solvent is the nucleophile. Solvent acts as a nucleophile. It needs to be weak, otherwise it will do other chemical reactions, and it is often a weak base like water or an alcohol. So stabilizing the resulting carbocation implies that the reaction goes faster, and 2 of the common solvents that can stabilize the carbocation and also are weak nucleophiles are water, an acetone, or an alcohol like methanol, ethanol, propanol, alcohols like that. So let's do a practice exercise. And for SN1 reactions, we go through a carbocation intermediate. So let's determine which of these carbocations are the most stable. Let's start off here at the top. Here I have a tertiary carbocation, here I have a secondary. Therefore, the tertiary is going to be the most stable. If I look down here at the next one, I have a tertiary versus a tertiary. The only difference here is I've drawn them differently, so those are actually the same. They're the same molecule. If I look down here, my carbocation, that would be one removed from a fluorine but tertiary. This would be one removed from a fluorine but it's only secondary, so the tertiary would be most stable. Here I look at these two and I realize that I have an electron withdrawing group. Here I'm secondary but one carbon removed from my fluorine. Here I'm secondary but two carbons removed, so they're both secondary, but I'm further away from that electron withdrawing group, that electronegative group, so this one is more stable. Here I have two molecules where I have a tertiary carbocation and a tertiary carbocation, but this one is right next to a nitrogen which can form a resonance structure. So in this case, this is going to be most stable. This one cannot form a resonance structure. And finally down here, and if I look at these secondary, tertiary, so now I'm not sure because this one's also allylic, isn't it? So this one's allylic, secondary allylic, and this one's tertiary but not allylic, so they're similar. I would have a hard time deciding which one of these two would react faster. Let's look at some solvent effects. So in a SN1 reaction, the first slow step is actually formation of the carbocation. And what I'd like to do is actually stabilize that carbocation. Okay? And if I can stabilize the carbocation with my solvent, because my solvent is my nucleophile here, then it will react with that carbocation. So let's look at some relative rates. So if I look at these polar product solvents are typically the best because they can stabilize both my carbocation and stabilize my leaving group. And if I looked at the relative reaction rates, and I just call acetone my relative rate of 1, so here's my solvent, and which acts as my nucleophile. If I go to a polar product solvent like ethanol, my rate increases by 200-fold. If I go to a smaller molecule, methanol, I increase 1,000-fold. And finally, water here, where my dielectric constant is much higher, I increase my rate by 8,000-fold. If I go to nonpolar molecules, aprotic nonpolar, my reaction rate decreases significantly to the fact where if I use hexane as the solvent, it does not react at all. So dielectric constant is sort of a measure of its ionizability and its polarity. SN1 reactions, because they go through a carbocation intermediate, that carbocation intermediate is trigonoplanar, which has ramifications for its stereochemistry of my product. The fact is that I can actually attack from the top side or the bottom side. So I either can retain my stereochemistry or I can go through inversion. The bottom line is I typically form a 50-50 racemic mixture of both molecules, stereochemical molecules. Let's look at that from a molecular orbital standpoint. So here I have a tertiary carbocation. It started out as a tertiary alkyl halide. In this case, my solvent is ethanol, which also acts as my nucleophile. If I attack from the top, I get the S stereoisomer. If my ethanol attacks from the bottom, I get the R stereoisomer. I form a 50-50 racemic mixture of these two. That's not quite true. If I look at this molecule, this bromine is still hanging around here and might get in the way of this ethanol. So there's a slight increase in this bottom molecule because attacking from the bottom side is a little bit easier if that bromine is sort of hanging around there. Okay, so it's not quite a racemic mixture. It's very, very close though. So in practice, there's usually more inversion product formed than the product with retention. So let's look at this example. Here I have a 5-membered ring. I have a bromine which is on the same side of my ring as this deuterium, the isotope of hydrogen. When I add methanol to this product, I lose my bromine, I form the carbocation. If I have bromine still in the vicinity, it has a hard time attacking. So it's a lot easier to attack from the bottom because it's not as hindered, if you will. And so I finish the reaction. In both cases, I have to deprotonate the resulting molecule. In one case, I get the cis stereoisomer, in other words, retention. And in the other case, I get trans, and I find out that I get 60% inversion, attack from the backside, and only 40% attack from the top side. The theory is that the bromine is still hanging around. When we have any reaction that has a carbocation intermediate, that carbocation is short-lived, and but it's very reactive, and it often goes through a rearrangement process to form a more stable carbocations. This is one of the drawbacks of an SN1 reaction. If you remember back a few chapters, if I have a secondary alkyl halide and I form the carbocation, and next to it I have a hydrogen that can hydride shift to form a tertiary carbocation, that happens very fast. Okay, so if I have the ability to form a more stable carbocation, I will do it. And one of those is a 1,2 hydride shift. Carbon 1, carbon 2, I shift my hydrogen over there to form a tertiary carbocation. And then that goes on to do my nucleophilic attack of my carbocation to form my products. Under the right conditions, I can even have a carbocation form on a primary alkyl halide. And that happens if I have some way of making a more stable carbocation. In this molecule here, if I lose the bromine, that's a primary carbocation, and I have no adjacent hydrogens to do a hydride shift, I actually can undergo a methyl shift in this case to form a tertiary carbocation. More stable carbocations are formed if I can. Let's do a few practice problems with the rearrangements. So I started off with a primary alkyl halide in this top case, and I formed a primary carbocation, which we know is not stable. And so I look for ways to make it more stable. I have a hydrogen right next door on the next carbon. If I do a hydride shift, I would actually form a secondary carbocation, which is more stable. Now that I've formed this secondary carbocation, I actually have hydrogens over here too. But if I did a hydride shift, I'd go from secondary to secondary, and there's no energetic reason for doing that, so this is my most stable carbocation. If I look down here at this second example, and I had a secondary alkyl halide, I lost that halogen to form a secondary carbocation, and if I look next to it, I can see that I have a hydrogen here, which if I did a 1,2 hydride shift, 1 to 2, I'm actually going to form a tertiary carbocation, which is more stable. This carbon right here also has hydrogens on it, but I'm not going to do a hydride shift from here, because if I do that, I go from a secondary carbocation to a secondary carbocation, and there's no energetic reason for doing that. It's energetically unfavorable. If I look finally down here at this example down here, I have a secondary carbocation. If I did a hydride shift from here over to that carbocation, I'd go from a secondary to a secondary, but also I'd go from a secondary to an allylic, which is more favorable because it's more stable, because I can draw a resonance structure here. So I would undergo a hydride shift to form an allylic carbocation. Rearrangements of carbocation. Let's look at another example. If I look at this carbocation, it's a secondary carbocation. When I think of rearrangements, I first think of hydride shifts because they're easier. There's two hydrogens here. I could do a hydride shift. But if I did that, I'd go from secondary to secondary. That is not energetically favorable. They're the same. There's no hydrogens over here to do a hydride shift, but there is a methyl group. And so I look at doing a methyl shift to actually make a tertiary carbocation. If I look at this example, somehow this molecule rearranged to form these three carbocations, and look how that happened. And I'm going to sort of put them all up at the same time. If I look at this molecule here, I've just sort of shown how that carbocation reshifts. So I've literally taken this carbon right here and I've shifted it up, even though it's in a ring structure, to do a 1,2 alkyl shift. If I look at this molecule, I just did a hydride shift because there is a hydrogen right here, so I did a 1,2 hydride shift to form this one. And this bottom molecule here, I actually did a 1,2 alkyl shift, but used this carbon down here, so I moved this one up to here. And again, I've just sort of redrawn that, and then redrew it again. And then I did a hydride shift. So here I have it a secondary alkyl halide, which is more stable than a primary, but I can undergo another rearrangement, do a hydride shift to form a tertiary alkyl halide. Very complicated stuff. The way they discovered that is they took this molecule, which had a halogen here, put it in solvent like methanol or water, and they found products for all four of these carbocations, including this one, so they formed 5 different products, and then they drew up a mechanism for that, and it explains the chemistry. So let's look at carbocation rearrangements again. In this case, let's draw a mechanism. So here I have a secondary alcohol. That's a poor leaving group, but if I protonate it, I can make it a good leaving group, and bromine becomes a nucleophile. And what I see is I find 2 different products. I can sort of see how this one worked here. This leaves and my bromine attacks that carbon. But this one here, I actually see that it must have undergone a rearrangement because I see a methyl group here now and my bromine is actually attached here. So to understand carbocation rearrangements, we often have to look at the product mix. So let's draw a mechanism for that. The first thing that's going to happen is I'm going to protonate my hydroxyl group to make it a good leaving group, and then it leaves. In the case here where I am blue, I have a secondary carbocation, okay, which then, if I did a hydride shift here, I'd form another secondary carbocation, so that's not the correct rearrangement here in blue. That doesn't happen. But if I do a methyl shift, I can form a tertiary carbocation, which then reacts with my bromine to form the end product here. However, there's always time involved in going to the most stable product, the major product. So there's always some time which I'm going through these green molecules here, where my initial carbocation can react with the nucleophile to form a minor product. So I always have major and minor products, and I often have rearrangements in SN1 type of reactions, making it a very messy type of chemical reaction. Let's look and compare an SN1 to SN2 energy diagram. SN2 is a concerted reaction. I have to have both my nucleophile and my alkyl halide come together, so I'm making a bond and breaking the bond in a transition state. In an SN1 reaction, my first step is to lose my halogen to form a reaction intermediate, and that's the slow step because it's high in activation energy, and then very quickly go over there, react with my nucleophile. I can get the same product in both cases. Turns out that typically SN2 reactions I get one major product. SN1 reactions I get a racemic mixture, and I also get rearrangements. So there are advantages of choosing my reactants and my reaction conditions carefully to control what type of chemical reaction I want the alkyl halide and the nucleophile to undergo. So let's look at some of the reaction conditions so that I can actually direct whether I undergo SN1 or SN2. SN2 reactions like to go with either primary or methyl alkyl halides, where SN1 reactions, the ones that form carbocations, they're very favorable for tertiary alkyl halides. Notice both of them can have secondary alkyl halides, so we tend to think of those as the problem child. They can undergo both SN1 and SN2. For SN2, I need a strong nucleophile, typically charged with a lone pair of electrons. For SN1, we call it solvolysis because it has a weak nucleophile, which is often the solvent. To promote SN2, I want to have an aprotic solvent. To promote SN1, I have a polar protic solvent to stabilize both my carbocation and stabilize my anion. In SN2, my rate is actually bimolecular, so I need to have equal concentrations of the alkyl halide and nucleophile, where in the SN1 reaction, I can add my nucleophile slowly after I form my alkyl halide because the rate only depends on the amount of alkyl halide. So it's bimolecular versus unimolecular. SN2 is a concerted reaction. SN1 is a stepwise reaction and often contains a third step, which is deprotonation of either the water or the alcohol. When I do an SN2 reaction, I get inversion of the chemistry at the if I have a chiral carbon. In solvolysis, SN1, I get two products, usually in nearly equal concentrations. And in SN2, I do not undergo any rearrangements. And solvolysis, I have rearranged products. So I get a lot of products here for SN1 solvolysis reactions. Having said that, there are some times where I just need to use an SN1 conditions to get the product that I need, and then separate out all the different products from each other using some sort of chromatography or separation technique. So for each of these chemical reactions, let's determine whether we predict that it's going to undergo an SN1 reaction or an SN2 reaction. So I need to look at both the substrate and the nucleophile. Let's redraw the molecule here. It makes it easier to look at. So in this case, this would be a tertiary alkyl halide, and this is a weak nucleophile. So this would undergo SN1 reactions. Let's redraw this one. Okay. So this is a primary alkyl halide, and this is a very strong nucleophile. Those are ripe conditions for doing SN2. So here would be my product. In this third example here, I'm going to redraw it again. This is a secondary alkyl halide. I know that can undergo SN1 and SN2, so I'm now going to look at my nucleophile and recognize that it's weak. It's just an alcohol or the solvent, so this undergoes SN1. And if I look at the product mix, if I did the experiment, I see that I must have undergone some rearrangement too. So this is a complicated reaction here. I first formed my carbocation, and then I had a hydride shift over to that carbon to form my more stable tertiary carbocation, and then I was attacked by the solvent. Let's look at this fourth example here. That's a secondary alkyl halide. Both SN1 and SN2 are capable. I then need to look at my solvent, which is weak, so I think SN1, and I think solvolysis reaction SN1. Here I have cyclohexyl bromide. Let's draw that. It's also the same as the one up above. In this case, however, I look at the nucleophile, and it's a very, very strong nucleophile. So I think SN2, and in this case, I get a product where I've substituted my strong nucleophile for the bromine. Very similar to the product mix I get up here, in this case with ethoxide, and this one with methanol as my nucleophile. Here's a chemical reaction, and if I take this secondary alkyl halide, I react it with methanol with a little bit of heat, I find out that I get several different products. I get a racemic mixture where I have a ether at carbon number 2, and here I have an ether at the third carbon from the right. So obviously this is going to be an SN1 reaction. We're just going to propose a mechanism. Let's start off with the first one here. So the first thing that happens, I leave and I form my carbocation, and then my solvent attacks that carbocation, and then I deprotonate that. I could attack from the top or the bottom, so I get a racemic mixture. On the top example here, I'm thinking rearrangements. So let's form our carbocation, and then let's do a hydride shift. And then let's see if that resulting carbocation is more stable. Yes, it's actually benzylic, which is more stable than secondary. So I have a more stable carbocation. I have attack from both the top and the bottom of my resulting carbocation. I deprotonate that to form this second product. I can actually use mechanisms that we've developed in this chapter to actually rationalize the product mix that I would see experimentally. In that last reaction, how would you expect the rate of reaction to change if we change the substrate to chlorine? Would it go faster, or would the process go slower? It would go much slower. That's because chlorine is a poor leaving group. If I looked at this molecule, if I went from the bromo substrate to the iodo substrate, it would go faster because iodine is a better leaving group because it's polarizable. If I went from the bromo compound to its stereoisomer, that would have no effect. So stereochemistry at the alkyl halide has no effect on the product mix because I first just lose that and form the carbocation. What if I change the solvent to ethanol instead of methanol? Ethanol is a little bit weaker nucleophile, so my reaction would slow down. It's not as solvating, and of course I formed different products.